So all of this together will let us explain and talk about periodic trends. So these are trends in characteristics of the elements, and they depend on two things. The first thing they depend on is the n level, by which I mean which n level are the valence electrons in. If you have a larger n level, right, those higher energy levels, those are farther away from the nucleus. That will affect things like how easy it is to take them away. How we can also, we'll end up talking about how, and anthropomorphizing them, how happy is an atom to get an extra electron. The second thing that we use to explain the periodic trends is something called the effective nuclear charge. So the n level, we have been working with this for a while, and we know how to find it from the periodic table. Effective nuclear charge, we call it ZEFF or Z with a star because it is based in the atomic number. Right? It is related to the number of protons that are in the nucleus pulling on the electrons, but it doesn't end up being perfect, which is why we call it effective. So effectively, how much pull does an electron feel from the nucleus? That's the effective nuclear charge. So it's the actual charge experienced by an electron related to nuclear charge, and then the factor that connects the two is shielding. So how much other electrons block that pull from the nucleus. So we're going to use Coulomb's law, and we're going to draw some pictures and whatnot, but in general, what you're imagining is the nucleus is at the center, it's a bunch of positive charge, it's pulling on the electrons. If you have a bunch of electrons outside the nucleus, the ones that are in between the nucleus and the valence, which is the outermost level, they're going to get in the way, right? The core electrons closer to the nucleus, they feel a bigger pull, but they also repel other electrons. And so it's the combination of all of those forces that gives us effective nuclear charge, right? You can't just say that because there are 35 protons, an electron feels a pull of 35 plus. That's a pretty strong pull, right? It has to be accounted for amongst all of the other electrons that are out there. Coulomb's law will help us with this. So this force, I think I have the force equation. You can also talk about this as an energy equation, which has some small tweaks. The 1 over 4 pi epsilon naught, those are all constants. The things that will change that we'll want to factor in are Q1, Q2, which are the charges on the particles, and then r squared, which is the distance between the particles. So the larger the magnitude of the charge, the stronger their interaction, either attraction or repulsion, and then the closer together they are, the stronger the attraction or repulsion. In this, right, the only thing that would affect the sign of this force is the signs on the charges. So same charges repel each other. So a positive times a positive or a negative times a negative would give you a positive value. So positive force is repulsive and a negative force is attractive. In something like lithium, so we'll start kind of small, right? I've got 3 protons in the nucleus. Then I've got 2 electrons in the 1s orbital, 1 electron in the 2s orbital. That 2s electron, it's farther from the nucleus, it's at a higher energy level. We know this because of the principal quantum number. So what we have is the 1s electron feeling a really strong pull. Like you pick one electron and say, what is the pull from the nucleus? So pick one of the electrons in the 1s, look at what it's interacting with, and it's getting pulled in by the nucleus pretty tightly. The 2s electron, it does feel that pull from the +3 that's in the nucleus, but it's also feeling a repulsion from the electrons that are in the 1s. So what we're saying is that the sum of +3 attraction and -2 repulsion is about a +1 net attractive force toward the nucleus. We call that the effective nuclear charge. The repulsion is known as shielding. It's sometimes also called screening. You can calculate effective nuclear charge, where you take the actual nuclear charge and then you subtract the amount by which other electrons screen or shield that electron from the attractive force. It uses something called Slater's rules. You don't have to do it until you get to inorganic chemistry. So if you aren't taking inorganic chemistry, you'll never have to do it. But there is a way to calculate for it. The main points that you want to take out of it is that this is why, as you get farther from the nucleus, the electrons are not as tightly pulled in by that attractive force. And the screening or shielding isn't perfect. So what we're going to see is that there are some changes in what you would expect in things like the size of the atom because of the effective nuclear charge. So let's do a trend in the periodic table. What we're going to do is talk about the trends, which you might have heard, you might already know, and we are going to talk about why that trend is the way it is. Now, overall in the periodic table, without applying this to a characteristic, as you go from left to right, the effective nuclear charge increases, right? If we're in a row, N stays the same. But what we're doing is, like, from element to element, you're adding a proton to the nucleus and then you're adding an electron. Screening is not perfect, so the extra electrons that are in there don't perfectly block that full 1+ charge that you have added. So the effective nuclear charge increases when you go from left to right. When you go down a column, the effective nuclear charge stays about the same, but the N increases. So the distance from the nucleus for that electron increases by an entire shell of electrons. Now, lots of stars, lots of highlighting. If I give you a trend and there is an exception and I have asked you to explain the exception, write the electron configuration and write an orbital diagram of the valence electrons, and this will help you explain it. Okay, so trends in the periodic table. Size of the atom is a trend. So we call it atomic radius in the realm of talking about our trend. From top to bottom, the atoms get bigger, right? Increasing the principal quantum number, we're adding shells of electrons. The outermost electron keeps getting further and further from the nucleus. That's a bigger atom. However, when you are in a row, so going across a row, the N doesn't change, but the effective nuclear charge increases. So that's because that effective nuclear charge is between negatively charged electrons and a positively charged nucleus, that's going to pull the electrons in tighter. It's an attractive force. So the atoms get smaller. The radius decreases as you go from left to right across the periodic table. Another trend that will be important is ionization energy. This is removing electrons. These values will be positive because you have to put energy in to take away an electron. Even right when it wants to give up electrons, you still have to overcome the attractive force that exists. So the trend that I'm going to give you in general is for first ionization energy. and we'll give some definitions of like, what does that mean? So first ionization energy means taking an atom and pulling away one electron. So we're turning it into a 1 plus cation. Across a row, so from left to right, the ionization energy increases, the first ionization energy. So imagine we have lithium and we have fluorine as the two extremes on row 2. Imagine taking an electron away from lithium versus taking an electron away from fluorine. Well, we know that lithium is going to be pretty happy to give up that electron because it does all the time. It forms lithium plus 1 cations. Fluorine, forming a fluorine 1 plus seems unheard of, right? You know that it likes to get an electron and be a negative ion. So the reasoning for that is the increase in effective nuclear charge, right? The electron that we are trying to take away is pulled on more tightly by the nucleus as we get to the right side of the periodic table. Now, from top to bottom, we only have to worry about how far from the nucleus is that electron. And so now we're worried about just the distance portion of Coulomb's law. Farther away means that it's a weaker force that we have to overcome. So the amount of energy we have to put in to remove that electron goes down. Now, this is a trend in first ionization energy. Trends in the other ionization energies aren't kind of universal across the periodic table and will depend on the electron configuration. So this is where you might need to write it. To help you kind of place what each ionization energy means, the first ionization energy means that you create the 1 plus. So you go from a neutral atom to a 1 plus cation plus the electron. The second ionization energy is creating the 2 plus. And each ionization energy refers to just taking out one electron. So the second ionization energy is the 1 plus cation giving up an electron to form the 2 plus. The third ionization energy is the 2 plus giving up an electron to form the 3 plus. So third ionization energy forms a 3 plus. If you are looking at a series of ionization energy values and you see one that is suddenly huge, like 10 times greater than the previous ionization energy, look at the electron configuration because you might just be trying to take away an electron from something really stable like a noble gas. Okay, let's talk about one more periodic trend and then one more general trend. The last trend that you'll see in the periodic table, or sort of represented that we can generalize, is electron affinity, which is the inverse, opposite, not reverse. It's the other thing. So ionization energy made cations, electron affinity makes anions. So take an atom, put in an electron, get the negative ion. The electron affinity can be positive or negative, right? If it's positive, it means like you are forcing that atom to take the electron. You have to put in energy to get it to stay. It doesn't really want it. Negative means the atom gave off energy when you put the electron in. It's happy to take that electron. So, right, the way that I have this written for electron affinity from left to right, it gets more negative. It could start out positive, right? I don't have the values here, but as you go from left to right, the atoms become happier to get that electron. So there might be a switch, or you might not have to put in as much energy. But the reason for this, again, every left to right trend is effective nuclear charge. When you put the electron in, it feels a higher pull from the nucleus, right? We've got a higher effective nuclear charge felt by that electron. It gets pulled in closer to the nucleus, lower energy. electron affinity down a column becomes more positive. So we're moving in a, like, I need to put in more energy to get this electron to stay value. And it's just because that the N is increasing, that added electron is farther away from the nucleus. We tend not to talk about second electron affinities in terms of trends. It doesn't necessarily help us figure anything out about the atom, though, like, there will come a point at which we might use a value for a second electron affinity. We're just not going to have to worry about it with the trend. The last piece to talk about in terms of size that's related to all of these factors is ionic radii. So what we need to know and think about for cations and anions, if you take an atom and you turn it into a cation, the cation will be smaller than the neutral atom. If you take an atom and turn it into an anion, the anion will be larger than the neutral atom. So I have some examples here for us to see it with exact sizes. So lithium versus lithium 1+. Lithium has 3 protons, 3 electrons. Lithium plus has 3 protons, 2 electrons. So imagine how strongly 2 electrons feel pulled toward a 3+ charge compared to 3 electrons pulled toward a 3+ charge. You would expect a much stronger attraction, which gives us a smaller radius, which we see if you look up the actual published data. Lithium has a radius of 152 picometers. Lithium plus, it's like 60 picometers. It's much smaller than the neutral atom. And this is exaggerated as you go to a higher cation charge. So beryllium, 4 protons, 4 electrons. Beryllium 2+, right? This is in the second column. It likes to form 2+ cations for electron configuration reasons that you now know. 4 protons pulling on 2 electrons. So that's a lot of effective nuclear charge. That's a really strong attraction, a very strong pull. Neutral beryllium is 112 picometers radius. The beryllium cation is 31 picometers. Let's look at a couple anions. Fluorine is 9 protons, 9 electrons. Fluorine with a 1-, so fluoride, is 9 protons, 10 electrons. So now I have 9+ charge, and it's trying to hold on to 10 negative charges. Now, right, we have stability from this. Otherwise, we wouldn't see it as often as we do. We have stability in the electron configuration because it gives us a noble gas configuration, but we still have like these basic laws of electrostatic attraction that apply in this situation, and it's just 9 protons cannot hold on to 10 electrons as tightly as it did 9 electrons. So fluorine has a radius of 72 picometers. Fluoride has a radius of 136 picometers, so it's bigger than the neutral atom. For oxygen, which we know likes to form -2 ions, 8 protons, 8 electrons versus 8 protons, 10 electrons. So now an 8+ trying to hold on to 10 electrons, we would expect it to be a lot bigger. Neutral oxygen is 73 picometers. O2- is 140 picometers. And then I want to point out, right, remember in our normal atomic radius periodic trend, as we go from left to right in a row, the atoms get smaller. And I've got arrows here just pointed at fluorine and oxygen. Fluorine is to the right of oxygen, so it should be smaller. And it is by a picometer, right? We've got 72 picometers for fluorine, 73 picometers for oxygen. But lithium and beryllium are in the same row. Lithium is 152 picometers at the beginning of the row with only 3 protons and 3 electrons. Fluorine with 9 protons, 9 electrons at the end of the row is 72 picometers. So you can see exactly like it is a distinct difference in atomic size in this trend.